Rev, we met very briefly at the GTC in Paris a few weeks ago, and it was a bit loud there, so we decided to have a little chat one-on-one here. So thanks for taking the time, and I would like to maybe give you the opportunity for all those who are living underneath the rock to introduce yourself shortly, and then I have a few questions for you. I would like to dive a little bit deeper into what you guys are doing.
Thank you for interviewing me. This is an honor and a pleasure. My name is Rev Lebaredian. I've been at NVIDIA for almost 24 years now. I lead the Omniverse and simulation technology group at NVIDIA. While I've been at NVIDIA, I've worn many hats. The first part of my time there has been largely about gaming technology to do simulation for entertainment purposes. But in more recent years, for about the last decade, I've been applying all those technologies to build physical AI, essentially uh, the AI necessary to build the brains of robots. In order to do that, we use a lot of simulation, and so that's what I work on these days.
Yeah, you would just mention that, and I would like to put my finger here on this as well. So you've been there. What you're doing now mainly for, you said, over a decade now, and so maybe you can tell me a little bit about what's the biggest shift when you see how like, physical products are being designed and validated compared to 10 years ago, and how the Omniverse is like accelerating that shift.
NVIDIA has been designing products that are physical for a long time. I mean, basically, we started by designing chips. And
Mm,
in some ways, you can think about a chip with the today hundreds of billions of transistors in them as essentially the most complex physical thing you can build. The the way we've built them from the start is by using simulation first, because that's the only way we know how to build them.
mm,
Our chip designers, even if they try, they can't sabotage our chip design because we have, from the beginning, essentially a supercomputer running that's continuously simulating the current design and testing it against all of the possible ways it might be used. And if some change is submitted to the design, it will likely fail and so won't be accepted. When we tape out our chip design and send it over to the foundry, to TSMC, it comes back and it just works because we simulated it so much, we emulated it, we are confident that this extremely complex machine with hundreds of billions of moving parts is going to work because we had simulation. We could predict the future of how it's going to behave. Our thesis is that everything that we are now building in all the other industries in the real world are approaching the same level of complexity as our chips and our software.
mm,
And so the only way to design a complex physical system that has lots of software in it these days,
mm.
something like a factory with automation and robots and many dimensions of moving parts in there, and ensure that it's going to work the first time when you bring it online, is by doing exactly what we've been doing with our chips. You have to simulate it all the way at the beginning. You start from the design and all the way through. So the biggest shift that we're seeing is now that the complexity of the systems we're building in the physical world, with the introduction of software into the systems, and most especially with the introduction of AI and physical AI and robotics into them, they're so complex that it's now become a necessity that you simulate them first before you deploy. If you're going to build a factory, $1 billion factory that has 1,000 autonomous robots in there and go deploy that system, you want to be sure that those robots are going to behave well before you put them out into the real world. and you're not going to have downtime in your factory, and they're going to be safe. The only way to do that is by testing them and simulating them in the virtual world. So this is the biggest shift we're seeing. The industry is starting to understand this, and so the ones that are on the frontier of building physical things are adopting simulation first strategies, and we've been anticipating this was going to happen, and that's why I shifted from applying simulation to entertainment and video games years ago to building a simulation operating system we call Omniverse almost 10 years ago, anticipating that this was going to happen and we're going to need more and more simulation to build everything in the world.
You were talking about factories, and so especially traditional manufacturers, it's a big topic at the moment, right? Everyone is going back to hardware and producing things. And traditional manufacturers, like those using heavy casting, I worked for Siemens in Berlin. They're producing large gas turbines years ago. And so this is huge and massive and made out of 10,000 pieces, right?
Those
So
are miracles of
yeah, of
engineering.
engineering. Actually adopting those simulation tools for those traditional manufacturers, I mean, the majority of them had been gradually going into this, right? So, but I mean, from your perspective, so what's working and what's not working using that kind of simulation?
Um, so simulation has been used and it continues to be used in engineering and design for many things. You know, we don't design airplanes and airplane wings without doing a lot of simulations in virtual wind tunnels, and uh, same with designing cars and designing many things. Um, but we've been limited by how much simulation we can do because it's a very specialist niche kind of skill
Hmm.
to be able to take the designs of the thing you want and go simulate the specific thing that you need. There's not many people in the world that know how to do it. It's very hard to
Hmm.
set it up. The other problem that we have is when we do these simulations, we're generally only simulating one aspect of the physical thing. There are the design of a physical thing, something like a car or an airplane, involves large teams with heterogeneous sets of skills. You know, one team might do the body, another team does uh, pieces of the engine, others do the electrical, others, you know, there's so many different aspects of it. And simulating all of it together is essentially impossible because the data that represents the digital version of this thing is never combined. We have like layers of the digital twin, all in different tools and different formats. So, what we're starting to see a shift with is first we're unifying all of the different aspects of the design of the physical thing, all the different layers of it into one form. We've been trying to push for this for a while, and now we're getting some real traction. That's essentially all of our work in the OpenUSD and the Alliance of OpenUSD group, where we're trying to create a unified representation of every aspect of a digital twin. And the next thing, the problem of uh, expertise in running simulation being a bottleneck, that's starting to change because with the advent of AI and particularly agentic AI, we can now bridge that gap, the skills gap between people that need to run simulation, which is essentially every designer, every operator, every person using a physical thing might need to run simulation. We can augment them with agents that are simulation experts that can help them go set up those simulations and run them.
Hmm.
If those designers who were building the turbines that you were working on, if every single person in that team had access to a team of simulation engineers who could on the spot set up and run a simulation for them to answer a what if question the designs you would build would be orders of magnitude better.
You already slipping into the next question because let's see. Hmm. You're already slipping to the next question. I work a lot with AI and robotic startups. So you were talking about teams, right? And how complicated and how vast the workforce needs to be to handle all those, right? And my question is, so for, let's say, for robotic startups building embodied AI agents, how they can leverage Omniverse without needing the full-blown simulation team. You were just about to explain a little bit more, but here I wanted to form the question more concrete.
The this modern AI was born about 12 years ago with the creation of AlexNet. That was the first
Mm,
deep learning neural network that was born on our GPUs. That ushered in the first era of AI, what we call perception AI. This is where we made very specialized neural networks that were very specific in what they did. You know, they can do certain kinds of image classification or understand certain kinds of audio and so on. It was mostly about computer vision and perception. The next era came in with generative AI, with the invention of transformers, LLMs. We now created more generalist AI models that have general information. They can do a lot of different things and have a kind of foundational knowledge built from a lot of training data, a lot of raw data about their context. Largely, these generative AI models we built were about the abstract world of language, of of things that are just naturally just information, the most naturally digitized things, what we can go find on the internet. We're currently entering the next era, which is agentic AI. This is where we're taking these models largely based on data from the digital world, which is abstract knowledge, books and text and these sorts of things. And we're creating essentially knowledge robots. They're like the equivalent of knowledge workers like you and me, where mostly we work with the computer. We exchange information with each other, just like we're doing right now.
mm,
We're creating agents that can go do things for us, act as it like an employee or a worker inside a team, but work within the knowledge space. What's about to come is the next era, which we're calling physical AI. This is where we take those same agents and we take the same fundamental technology we use to build the brains for these agents, but we train them not just with information in the knowledge world, but information about the physical world. And we can train them with that information because we can generate that information from simulations about the physical world. Once we can create a good enough physical AI, we essentially have the elements we need to build a robot brain. And we can take those agents out of the computer, out of the internet, and place them inside a body, like a humanoid or an arm, a manipulator or an AMR or a car, autonomous vehicle. And these agents can interact with the world of atoms. Now, the question might be why should we do that? Why is that important? Well, if you look at what is of value to humans by looking at one measure of it, which is the size of our markets in the
mm,
world. The world of IT, the markets for IT is about $5 trillion maximum. This is largely where all of the big tech companies participate. They're in that $5 trillion space, which is a huge number, right? This is the NVIDIAs, Apple, Google, Amazons, all of them. This is where we largely participate. But total world markets, not IT, not about information, is over $100 trillion, which says that what we value the most, as valuable as information is, the manipulation of atoms is actually more valuable. So in that $100 trillion, we have industries like transportation, transporting people, transporting our goods in our supply chains. We have manufacturing, which is manipulating atoms, restructuring them into products that are of higher value than what we put into the factories. We have pharmaceutical production. We have surgery, healthcare. These are all things that are about atoms, moving atoms around. As big an amplifier of productivity as computing has been over the last 5, 6 decades, largely the industries that are about atoms have been unaffected by computing.
Which is crazy if you think about just the sheer numbers of it, right? You
That's
say
right.
this is a $5 trillion market. Everyone, the big companies are aiming for that. And that, yeah, guys, this is where the majority of productivity is coming from, like 5 trillion the last 20 years. But this is five, and this is like the rest of the
100.
100, right?
And the
So,
100's largely untouched. But with this new technology, with AI, and moving it into physical AI, if we can create AIs that understand the physical world, the world of atoms, we now have the opportunity to bring the gains that computing has brought to the information space
hmm.
into the physical space, the world of atoms. And so we can apply this technology and make it an amplifier for that 100 trillions. So the information space has grown by orders of magnitude over these decades. So you can imagine if we apply the same amplifier, the same technology to the world of atoms, we can increase our productivity orders of magnitude there. And intuitively, that makes sense. If we can build autonomous agents that operate in the physical world, that can do a lot of the work that only humans used to be able to do, work that's limited by our populations, we can potentially add physical laborers. These are truck drivers, uh, miners that work in dangerous, dirty jobs like mining or manufacturing, etc. You are essentially doing the equivalent of increasing the population of an economy, which will directly correlate with GDP. The more participants you have in an economy, the greater the productivity will be. So that's what's happening right now, and this is the opportunity in front of all of us. And a lot of what we're feeling here in terms of this crazy acceleration with AI is this. It's because it is really a profound unlock into applying this really powerful technology of computing into the physical world. That promise exists now that didn't 10 years ago.
Do you think, I mean, taking or putting the numbers aside, when it comes to the market that you're addressing, just the idea that this kind of acceleration happened now only to those who've been in front of a computer and a keyboard and a mouse, right? But now we're applying this to people that are not working in that kind of environment. And now, so this is, I think, what makes it the most exciting, the embodied part of the AI revolution, right?
That is a really astute point, and I think it's one that everybody should really think about and absorb. Um, Computing as big a value add as it's been to our economy, the people that have enjoyed that prosperity the most, people that have enjoyed the fruits of computing the most, are the ones that know how to actually build those computers and manipulate those computing systems to program them. And there's not that many of those people in the world. You know, by some measure, maybe there's 30 million programmers, software engineers in the world total, but there's 8 billion people on Earth. So most people on Earth have not benefited from it directly. But AI is essentially unlocking the possibility of every person on Earth being a programmer, because they can program it with just natural language. And so the fruits of computing can now be shared across everyone in a way that wasn't possible before.
Um, I do know that there's another question that I think is giving you the opportunity to dive a little bit deeper into the topic Omniverse. So a bit before that, just very shortly, I think this is something that I ran over very often during conversations. I mean, you have been in the space for over 30 years now. What is something that people still get wrong about simulation or digital twin?
Oh yeah, there's so many things that are confusing here because there are many sort of definitions of this, and everybody sees it not necessarily wrongly, but I think from a more narrow lens that comes from their particular industry, their particular skill set, and what's important to them in their particular profession. Um, I like to think of digital twins more expansively and simply. Essentially, the idea of a digital twin from our perspective is taking something that is in the physical world and representing it in the digital world in a simulation such that you can actually predict its behavior. If given the right conditions, the right inputs you give into that system, it will behave the same way. So you can make it predictive. So if I'm going to build a digital twin of my product, maybe it's a car, or I can bring that car into into my computer, have an abstract representation of that completely digitally, but then I can operate that car and it behaves exactly like it would in the real world in every aspect of it. So all of the dynamics of the vehicle should behave the same way. The software in the car should behave the same way. The infotainment system, every aspect of it. Now, in order for a digital twin to be useful, it doesn't actually have to do every aspect of it. Depending on what you're doing, you don't necessarily need to know what the infotainment system is doing if all you care about is it going to be aerodynamic,
Yeah,
right?
yeah, yeah.
But it is useful to have the combination of all of the different aspects of that car in one model that could be passed around all of the different departments inside
Globally.
the company that is designing it, and even for the end users of it. Before I buy that car, I might want to go test it out. I might want to test it out in my city, in my streets, and see how I might like it, for example. This pattern exists for everything that we build in the real world. You'd like to do that with your factories. You'd like to do that with your warehouses. We are doing that with the AI factories that we're building. Our data centers are very special. They're not like the old data centers. These are gigawatt factories now that we're building, and they're super complex. The only way we know how to build them on time, build them under budget, and build them so that they work and can operate at full efficiency is by simulating every aspect of it, from the power to the cooling systems and the wiring. Every aspect of it needs to be simulated first. And so this is I think how people should be thinking about it. The digital twin is just take every aspect of the thing that matters to you in the physical world, bring it into the computer, and use that just like you would use the real thing in the real world. You would use it, you would test it out in the real world if you had the physical thing. Now you can do it in the computing in the digital world, but do it a lot cheaper, a lot faster, and a lot more safely.
I think you just described my next question because It seems like this is your favorite use case, right? Using it for your own products, because the question would have been since the launch of Omniverse, what is the use case to surprise you the most, right? And changes everything. But I think you gave a pretty good answer to that. That using that, building that is helping you guys. It seems like a loop, right? So you're only able to build this kind of factories because you've built the Omniverse up front, and now you're being able to enhance the complexity and the depth and the complexity of it, right?
That's
To an
right. And we're
extent that
doing it
was
in two
unable
ways.
before.
We have a great many wonderful partners who help us build our computers. We don't build physical things directly. We design them, but we work with great partners like Foxconn and Wistron and Pegatron, all these electronics contract manufacturers to actually build these parts. And they have the most sophisticated and complex factories in the world. And they're introducing more and more autonomy into them so that they can deliver on on building what we need, these really complex machines, and doing that at scale. We There's great demand for what we're building, and so the speed and scale at which we're building them is unparalleled in the past. The only way we can do this is by simulating first. So we get to go work with our partners and give them our technology to help them build the factories to build the computers that we need to go build this technology. That's pretty awesome in and of itself. But then the output of this is um, is the core component of the AI factories that we're essentially building everywhere in the world. The fundamental infrastructure for the new industrial revolution. It's the intelligence infrastructure. Just like the last one was all about electrification and building the infrastructure for electricity, the new infrastructure is the intelligence infrastructure, these AI factories. And building those also requires an intense amount of simulation to both build and operate them, operating them peak efficiency. So that's probably been the most surprising one for me. We expected eventually we're going to have to do that kind of stuff, but it happened a lot
Mhm.
faster than we thought. We were going to apply. We are applying Omniverse to other types of factories and manufacturing, but given the great demand in the world for our factories, this has become a prime use case for Omniverse that was surprising how quickly it happened.
Being with a company now for, as you said earlier, almost 24 years, I was very excited that you said yes very quickly to our little chat. And I think what people really can feel and see is how excited you are, even after this time, right, with the company. Still excited for what's still coming for you guys. And I think this is something that it's infectious. I think when we met at the GDC, I think you can see people and talking and with clients and customers and partners, you see that there's some sort of excitement that you guys are spreading. And it was all about Europe and the AI infrastructure. I think Jensen made it very clear that yeah, there's a lot of conversations going on, not only with companies, but with governments as well. So I think here you guys are really pushing it and pushing the new revolution forward.
Well, I think what you were sensing, what you're experiencing, is a result of a decision that Jensen made at the founding of the company.
Hmm.
When founding the company, he was thinking about what kind of company does he want to build and what is it for? Most people who are founding companies start thinking about their mission
Hmm.
and mission statements. What are they going to build? What Jensen decided was that he wants to build a company where the best people in the world in computer science and computer engineering will come to do their life's work. And so doing that has a lot of, if you're serious about that, there's um, there are specific things that you need to do, and more importantly, things that you don't do to create the conditions by which people want to do that. And the key, I believe the biggest, most important thing that we do that's different from other companies is that we don't go and try to take market share from others.
Mm,
When a market exists and there is a company that is already doing something well there, we don't we don't make our engineers, our computer scientists, go figure out how to build that thing that's already been built, but do it cheaper, and more efficiently, because that wouldn't attract the people that would like to do their life's work. So we always do the opposite. When we see that there's a market that's becoming a commodity, we leave it. We only go work on things that Jensen calls $0 billion businesses. They're $0 billion because they're markets that don't exist yet. But we
mm,
can imagine that if we solve this problem that seems impossible by putting the best people in the world and dedicating their lives to that, it will unlock billions and billions of dollars in market. We'll create a new market. And as a result, you have many like me. I'm by no means special that I've been here 23, 24 years. We have many like me that have been here for this long or longer because we're all doing our life's work. This isn't about just making money. I mean, that's nice, but what really motivates us is doing something profound, and doing our life's work. And what could be more exciting and more fun than that? That's why we're all so passionate about it. And I think you're feeling that at GTC.
yeah. It was amazing. I mean, it was my first one. So, and I think it was the first one in Europe, and definitely not the last one. I'm excited to see what's coming. I know you guys are always cooking something, so I'm keeping. I think we all need to keep an eye on you. And I say again, thanks that you took some time out of your schedule, and we couldn't make the interview at the GDC, but I'm happy that you said yes for today, and I'm happy to see what's next for you guys.
Thank you for having me here. It was a pleasure to talk to you, and I hope we do it again soon.
Yes. Take care.
Thank you.
Bye bye.